Okay, folks, we are back. Let's talk about these last few problems in section 4.4. Problem 8 says we have at a high school festival. Get this over here out of the way. At a high school festival, Felicia has 3 tickets for the football toss, 4 tickets for the cakewalk, and 6 tickets for miniature golf. How many possibilities does she have to select the order in which to use the 13 tickets? So what we have here is an arrangement. They're put in order of 13 items where we have a fixed number of each item. So that is the multinomial coefficient. That is 13, choose 3, 4, 6. Which is 13 factorial over 3 factorial, 4 factorial, and 6 factorial. I'll take care of the 6 factorial, then 3 times 2 times 1, and 4 times 3 times 2 times 1. So let's see, 3 goes into 12 4 times, and there goes the 4. 2 goes into 10 5 times, 3 goes into 9 3 times, 2 goes into 8 4 times. So if I've done all my arithmetic correctly here, I believe that this is 60,060 different ways that can happen. Problem 9 says, okay, we've got 6 friends playing poker, each starting with $5. All bets are in multiples of 10 cents. So how many ways are possible for the redistribution of the $30 after the night of poker? And so we're assuming that enough hands take place to where someone could completely be completely wiped out at the end of the evening, because we need all possibilities here. Well, we have the thing that's kind of distinguishable here are the 6 friends, right? And so we have these, even though it's $30 in 10-cent multiples, there's 300, if you will, stars that are worth a dime each, and we need to figure out where to put our 6 minus 1 5 bars in there to split those things up. So if you like the notation, it is 6 separate things that we're reusing and a multiset of length 300. In other words, 300 stars and 6 minus 1 bars. Excuse me. So this is 305. Choose 300, which according to my calculations is 21,281,794,436. Okay, a lot of different ways. Okay. Then problem 14. Oops, I left 13 out of there somewhere or another. Oh yeah, here we go. This is where we have the basket of 3 red eggs, 8 green eggs, 5 blue eggs, 7 yellow eggs, and 4 purple eggs. And the question then is, how many ways may we distribute these to 8 children with no restrictions on the number of eggs each child receives? So this is actually pretty similar to a problem we did previously, where we say, all right, let's worry about the red eggs first. And now I've got 3 of those, so I've got 3 stars. And I need to determine how to place the 7, the 8 minus 1, 7 bars, representing, that gives us 8 categories here for each child. And it's a task with actually, 5 selections, right? So when we've calculated all these numbers, then we would use the fundamental counting principle to multiply them up and get the answer. So just calculating the number of ways to redistribute the red ones. Okay, now remember my bars are the different kids. So I've got 8 things here. I'm going to assign, I've got a child I'm going to assign to each of the things in a list of size 3. That's my red eggs. So 3 stars and 8 minus 1 bars. This is 10 choose 3, which is 120 ways of doing just the red ones. Okay, green, there's our 8 kids, and I have 8 green eggs. So 8 stars and 8 minus 1 bars. So this is 15 choose 8, which according to my calculator is 6,435. Look at the blue. Again, 8 kids. That's our categories, and I've got 5 of these that I can multi-choose. So that is 5 stars plus 8 minus 1 bars. 12 choose 5 is 792. Almost there. Let's do the yellow. 8 kids, and there are 7 kids. So 7 stars and 8 minus 1, 7 bars. Hold on to that bottom 7. So 14 choose 7 is, according to my calculations, 3,432. And then finally the purple ones. 8 kids that they will go to and multi-choose 4. So 4 stars and 8 minus 1 bars. 11 choose 4 is 330. So then the total is 120 times 6435 times 792 times 3,432, and then times 330. So this is a heap big number. 692 trillion, 653 billion, 2 million, 944,000. Okay. Great to big a number. Problem 14 has us doing some translations, but back and forth between these things. For example, with 5 kinds of donuts, that means I need 4 bars. 3 of type 1, ready for 2. There's 1 of type 2, ready for 3, none. Ready for 4, and there's 2. And then 1, 2, 3, 4, and that's it for the 5 kinds. With 6 kinds of donuts, we've got 0. I need 5 bars, so 0 of type 1, 4 of type 2, 0 of 3, 0 of 4, 0 of 5, and then there's 2 of type 6. There you go. With 7 kind of donuts, we got 3 of type 1, none of 2, none of 3. Type 4 has 4. Type 5 has 1, and there's 6 and 7. Then from the count, yep. So from the 5 kind of donuts, the way to get no donuts at all is to put 4 bars, and that's it. the stars and bars to words section of this is, okay, let's see. We've got, how many types? 1, 2, 3, 4, 5, 6. So there's 7 types. 2 of type 1. 1 of type 4. And then 2 of type 1, 2, 3, 4, 5, and that's it. In part I, double I, 1, 2, 3, 4, 5. So there's 6 types. 1 of type 2. 3 of type 4. 1 of type 5. And then 4 of type 6. Let's see, 5 bars, so there's 6 types. Let's see, 1, 2, 3, 4, 2 of type 4. And then the last one, there are 3 types, because there are 2 markers. 3 of type 1, 2 of type 3. Okay? And then lastly, give an explanation based on stars and bars to find the number of solutions to x sub 1 plus x sub 2 plus x sub 3 plus x sub 4 plus x sub 5 plus x sub 6 equals 7, where x sub I is a whole number. Okay, well 0 is a whole number, so we can think of this having, since the total of all these things is 7, having 7 stars, and we've got 6 categories here, and just do 5 bars. Or if you want to think of it like this, we've got 6 locations, categories that each of these 7 things can plug into. So this is 7 plus 6 minus 1 over 7. Yep, 12 choose 7, which I found to be 792. Okay. We still have a little bit of work to do with the multi-set supplement, but we'll do that in just a minute.